G'day team, welcome back. So we've been doing a fair bit of work with quadratics in different forms, so the equations of quadratics in different forms. We're now going to move on to graphing quadratics, and we're going to look at the information you can pull from those different equations that we have been looking at. First of all though, I just want you guys to be all over a few bits of terminology, okay? So you guys all know x-intercepts and y-intercepts, so x-intercepts are when the function cuts the x-axis, y-intercept when the function cuts the y-axis, okay? Couple extra little bits on here. So we have this line here called our axis of symmetry, all right? Doesn't really look like it on my diagram, but it cuts through the middle of our quadratic. So it's our axis of symmetry. So the left-hand side of our quadratic is a reflection in the y in that axis of symmetry to that right-hand side, okay? We'll also have a vertex, either a minimum or a maximum, depending on the shape of our quadratic. So in this case, we have a concave up quadratic, so we have a minimum. If we had a concave down quadratic, we would have a maximum. When you are graphing quadratics, please make sure you are labeling your function, you are labeling your axes, and you have the same scale for your whole x-axis and your same scale for your whole y-axis, okay? Those features are very important. So as I said, if your quadratic is concave up, so it looks like a smiley face, then you have a minimum turning point or a minimum vertex. And if your quadratic is concave down, he's got a frowny face, he's feeling down, then he has a maximum turning point or a maximum vertex, all right? So quadratics can be written in four forms. So we have our general form, ax squared plus bx plus c equals 0. A cannot equal 0, okay? Factorized form, so y equals a multiplied by x take p multiplied by x take q. P and Q are numbers in the real number set, and again, A cannot be equal to 0, so this will follow through for all of these forms. Form 3 is our vertex form, so y equals A multiplied by x take away h all squared. H is a real number and A is not equal to 0. And then finally we have our vertex intercept form, so y equals A x take h all squared plus k, where h and k are in the real number set, and a is not equal to 0, okay? So today we're going to be looking at these three forms here, so form 2, 3, and 4. So if you have a quadratic in factorized form, our quadratic is going to look something like this, okay? So hopefully you notice that I don't actually have a y-axis here, and that's because our quadratic might not actually cut the y-axis in our domain or our range that we are actually looking at. Okay, so our x-intercepts are p and q, so using that null factor law, solving for these terms, these linear factors to be equal to 0. Our axis of symmetry has the equation x equals p plus q on 2. So it's actually the average x coordinate of our x-intercepts, which makes sense because it is the middle. And then our x coordinate of the vertex is actually the axis of symmetry, all right? To find the y coordinate, you take this value, substitute it back into our quadratic, okay? So they're the key features of a factorized form quadratic. For a vertex form, all right, again, no y-axis just because it could be anywhere on our Cartesian plane, all right? So in this case, it touches the x-axis at h, all right? Doesn't cut, it touches. Our axis of symmetry is x equals h, all right? That equal sign shouldn't be there. So x equals h is our axis of symmetry equation, and our vertex will sit at h and 0, okay? Because it touches the x-axis, our y-coordinate is 0. So our graph will look something like this. Finally, for our vertex intercept form, our axis of symmetry, our x equals h again, but our vertex is at the point hk, all right? So if this is a negative here, then k would have the negative sign inside. And a quadratic in this form may be anywhere on the Cartesian plane, might not touch the x-axis, might not touch the y-axis where we're looking at, okay? So that's why there's no x or y-axis drawn in. For a quadratic function in general form, so y equals ax squared plus bx plus c, where a cannot equal 0, if a is greater than 0, then we get our concave up, which is our shape that looks like this. If a is negative or less than 0, it produces the concave down. All right, so if a question asks you what effect a has on a function or the shape, then you're looking at what sign the coefficient a is. If it's positive, concave up. If it's negative, concave down. If a is a positive or a negative fraction, all right, a cannot equal 0, the graph gets wider than our original function y equals x squared. All right, so it means if we're having a look at x squared, if we have a function, say a half x squared, then it would look something more spread out like that, okay? If a is less than -1 or a is greater than 1, then the graph will be narrower than y equals x squared, okay? So it has the opposite effect. Bit of an example, okay? So using axes intercepts, sketch the graph. So y equals negative x take 4, x plus 2. All right, so first thing I look for is my a value. In this case, it's -1. So that means we're going to have a concave down looking quadratic, okay? So that means we know what shape we're going to get. Our x-intercepts using the null factor law are -2 and 4, okay? So all we're going to do is plot that onto our graph there. So you can also find the axis of symmetry. So remember, axis of symmetry, x equals our two x-intercepts added together, so -2 plus 4 divided by 2, which equals 1. And as you can see, that's approximately there. All right. Awesome, awesome, awesome. So if you're playing along with the Hazy textbook, have a crack at questions in chapter 2D.1. All right, and we will see you next time. Thank you.